Hi, guys. So to start this unit about nuclear chemistry, we need to understand what radioactivity means. So let's look at what determines if an atom is stable or unstable. So up until this point, when we talk about stability, you guys are probably thinking about number of valence electrons, right? So an atom that does not have 8 valence electrons will try to bond with something else to get a full valence shell, and then the atom will be stable. As far as radioactivity goes, we need to talk specifically about the nucleus of the atom and whether it's stable or not. If the nucleus is unstable, then that means that that element is, or that atom is radioactive. So, what does it mean to be stable as far as a nucleus goes? We need to think about what the particles in the nucleus are, and those are protons and neutrons. The closer the proton to neutron ratio is to 1, the more stable the nucleus is. So once we start getting into heavier elements and our number of neutrons is very, very different, much higher than our number of protons, that's when we're going to start to get to unstable nuclei, and we can call those isotopes radioactive isotopes. So just like in a chemical reaction, where if the valence electron shell is not full, it'll do something to get stable, it will bond. An unstable nucleus is also going to do something to try to get more stable. And what it's going to do is it's going to decay. That's what we call it. And what decaying means is that your nucleus is going to emit or get rid of particles. And if the nucleus is changing its number of particles, then the atom is actually going to change into a new element, which is something pretty cool because it's something we've never seen this before, guys. When you look at chemical reactions, the same elements that are on the left side of the arrow are also on the right side of the arrow. They might be bonded to something different, but they're still there. We know it's a nuclear reaction if you look to the right side of the arrow and there's a totally different element there. Okay, so that's something that's kind of cool. This graph here is showing you this red solid line is if our proton to neutron ratio is 1 to 1. And this little fuzzy area here, all of these little red dots, these are actual elements and isotopes of those different elements as they appear on the periodic table. The number of protons down here, that's your atomic number, right? And then this graph, this side is showing us our number of neutrons. So you can see, guys, that as my elements get heavier, they are getting further and further away from that 1 to 1 neutron to proton ratio. Up here, we have mercury, where the ratio is 1.5 to 1. Again, the heavier you are, you can get away with being far away from that 1 to 1 ratio. But we do get to a point where polonium and higher. So if you guys look up the atomic number of polonium, anything heavier than that or with an atomic number higher than that is going to have no stable isotopes. So like mercury 200 is stable, and then there are other isotopes of mercury that are heavier that are unstable, but at least like mercury has 1 stable isotopes. Anything polonium or higher is going to be all radioactive, no matter what the size of the isotope is. Okay, so let's look at an easier example. If you guys remember isotopic notation, we're going to write the symbol of an element. So let's do carbon. And most carbon isotopes weigh 12, but I want you guys to look at carbon 12 versus carbon 14. Do we remember how to figure out the number of protons? We look at the atomic number, right? If you guys don't have your periodic table out, you will actually need it. So it's good to get it out now. So carbon's atomic number is 6. So whether it's carbon 12 or carbon 14, its number of protons is going to be 6. Do we remember how to figure out the number of neutrons? So the mass comes from the protons plus the neutrons. So if my carbon 12 has to weigh 12, I have 6 protons, I need 6 neutrons. What about for carbon 14? Hopefully you're figuring out that there's 8. So as far as being stable and unstable, this is going to be my stable version of carbon. This is going to be my radioactive or unstable version of carbon. So guys, if you think back to the atom unit and isotopes, um, why is like 99% of the carbon in the world carbon 12? Because that's the stable version of carbon. Does carbon 14 exist? Of course, but it's very unstable. So those carbon 14 atoms are going to decay over time. They're going to emit particles from their nucleus and turn into something else that's more stable. So going back to that atomic mass formula, you can understand why the percents of the ratio of the isotopes of the different elements, why they're so different from one another. There's usually like 99% of the one isotope, and the rest of them like barely exist. And that's because they're unstable. Okay, so radioactive decay. Natural transmutation is the nuclear reaction that we're going to talk about first. I want you guys to like circle this because this is important. And the important thing to know about natural transmutation is that it's a spontaneous decay. That word spontaneous is important. That means that it happens all by itself. It does not have to be forced. This nucleus is floating around and it's very unstable, and all by itself, it's going to get rid of a particle and turn into something else. How to spot a natural transmutation? They look very similar to decomposition reactions in that they have one reactant. That reactant doesn't need anything else to get going. It's just going to decay all by itself. Now, this reference table, table O, this is in the Regents reference tables. This is something that you guys you'll have to know the masses and the charges of these particles. So on this table, they give you the name, they give you the notation. Now, the notation has 2 numbers in it. The top number is the mass, and the bottom number is the charge. And that goes for all of the symbols in this table. They all have top and bottom numbers. And then this last column gives you just the symbol without its mass or charge. So this is the list of particles that an atom can emit in order to turn into something else. Okay. This is just another visual of those particles, those types of radiation that our elements that are radioactive can emit. Here specifically, we're looking at alpha, beta, and gamma particles, which are the most common for radioactive emissions. What's on this chart that we didn't really see up here, and actually like the Regents loves asking about this, is this penetrating powder. So you want to think like you want to think about size first, guys. So like let's say I'm trying to squeeze through a crowd, right? You want to think if you're a bigger person, you might have a harder time squeezing through a crowd, where if you're a smaller person, you can kind of turn sideways and make your way through a little bit better, like you're a little more agile, right? So it's the same thing with particles. Alpha particles have a bigger mass compared to beta and gamma particles. So as far as like squeezing through small places, they're not very good at it. So alpha particles have the lowest penetrating power of the 3. Beta is a little bit bigger. I'm sorry, a little bit smaller, but not as small as the gamma. So they're like kind of okay at squeezing through small spaces. Um, Gamma particles have no mass and no charge. They are the best They have the greatest penetrating power as far as like squeezing through. Aside from mass, you also can look at the charge. Because an alpha particle has a positive charge, if an alpha particle is passing through an electric field, it's going to be attracted or repelled. It's going to have a hard time going in a straight line, right? So if there's something negative, the alpha particle is going to like veer towards that negative thing. And same thing with a beta particle having a charge. If it's going by something positive, it's going to be more attracted to that instead of going in a straight line. The fact that the gamma particle has no charge, that's what makes it even better at having at penetrating things, at having a greater penetrating power. So you want to look at mass and charge when you're asked about that. Okay. This is just a visual of what I was just telling you about. We see that electrons, when passing through an electric field, they're going to bend towards the positive side because opposites attract. Protons, alpha particles, positrons, these are all positive particles. So they're going to bend towards the negative side of the electric field, where our neutrons and our gamma radiation, notice how they're traveling in a straight line. They don't have a charge, so their direction that they're traveling is not going to be affected by this, which makes them better at penetrating. Okay. And guys, this is a visual that we've seen before when we talked about radiation. This is just to give you an idea of, here we have our gamma rays, of the sizes of the waves, and how much energy they have. Okay, so again, these gamma particles, these are very high as far as energy goes, which makes their uses and their risks. This kind of helps us explain their uses and their risks, which we're going to get to in another video. Okay. Here's what you guys have to know how to do. I showed you table O. This is table N. And we kind of need to use table O and table N together to write out decay equations. So here I have calcium 37. And if you look at the calcium that's in If you look at the calcium that's in the periodic table, most calciums have a mass of 40, and that's like a stable version of calcium. Calcium 37 is radioactive, and if it's on table N, that's one way of us knowing for sure that it's radioactive. Now, what table N tells us, if we look in this column right here, the decay mode, it tells us what particle calcium is getting rid of in order to become a more stable nucleus. So calcium is on the left side of my arrow. That's my one reactant. And all by itself, it's going to get rid of a beta particle. Now, table N just tells us what the particle is. I actually have to go back to table O to know that a beta particle has a mass of 0 and a charge of +1. So once I use table N, I have to jump to table O to say, okay, well, what's the real symbol for that particle? Now, if you guys look at this bottom number, right? This is the nuclear charge of calcium, and up here is the mass. Just like in chemical reactions, in nuclear reactions, mass and charge have to be conserved. So my left side and my right side should weigh the same, and they should have the same charges. So if on the left side my mass is 37, and on the right side a positron has no mass, then the mass of my new element has to weigh 37. These two top numbers have to equal 37 because the mass on the left side is 37. My charge on the left side is 20, so on the right side, my charge has to equal 20. So if a positron has a charge of +1, then my new element that I'm making has to have a nuclear charge of 19 because 19 and 1 are going to equal 20. Now, how do I know that my new element being created is potassium? The nuclear charge is the atomic number. So if you guys go and look on the periodic table and you find atomic number 19, it's potassium. All right. So what are you guys going to have to be able to do? This is something that you're going to be given. You'll be given something that looks like this, and you'll be asked to write the equation. So first things first, I'm noticing that krypton here only has one, it only has one number with it, and that's its mass. I can easily go to my periodic table and look up the atomic number of krypton because you need both. Okay. Now, next thing I want to do is I want to find krypton on this table, and I want to look at its decay mode. I see a B minus, which means that its decay mode is a beta particle. It gets rid of a beta particle. I want to scroll back to table O and say, okay, beta particle. There's the symbol. Mass of 0, charge of -1. Mass of 0, charge of -1. You could either write the B or the E here, guys. It doesn't matter. Now, conservation of mass, conservation of charge. On the right side, my top numbers have to add to 85. If the beta particle has a mass of 0, then my missing element must have a mass of 85. Charges have to be the same on both sides. So if my bottom numbers over here have to add up to 36, I have a -1. So what am I going to put here to make a 36? A 37. If I go to my periodic table, I'm going to find which element has an atomic number of 37, and I see that that's rubidium. Okay, so that's how you do it, guys. I want you to give this one a try. So here's my missing pieces. I'll go ahead and help you out and give you the atomic number of TH. And I want you guys to figure out what particle gets emitted and what my new element is. Okay. So this little graph, guys, this is the decay series starting with uranium up here. So we're going to start with uranium. Now, uranium, every time you see an arrow, that shows that the atom is getting rid of a particle and turning into something else. So my first step in this decay series is uranium turning into thallium, right? So what they can ask you as far as this graph goes is they can ask you what the particle is that helps uranium turn to thallium. So it's the same thing that I did above, except I'm not using table N. I'm trying to find the particle using what they gave me. So uranium, if you look, this axis over here is the mass number. So uranium had a mass of 238 and it turned into thallium that has a mass of 234. So I'm going from 238 to 234. And atomic number, this axis down here is our atomic number. So uranium has an atomic number of 92. Thallium has an atomic number of 90. Okay, so what they're going to want to know is what particle had to be emitted in order to turn into TH234. So same thing, guys. My mass on the left side is 238. My mass on the right side has to add up to 238. So if thallium is 234, my missing particle must have a mass of 4. My bottom number over here is 92. My bottom numbers over here have to add up to 92. So what's the bottom number of my missing particle? 2. Okay. Now, guys, I'm looking for a particle here. So I don't want to go to the periodic table. I want to go to table O. and I want to say, okay, what particle has a mass of 4 and a charge of 2? That's my alpha particle. So you could either write He, because the alpha particle happens to be the same as a helium atom, or you can write the symbol for alpha. Whatever you prefer is fine. Okay? I want you guys to try the next one. So in the next one, I have thallium turning into Pa. And it does that by getting rid of some particle. So I want you guys to try that. Find the atomic number and the masses of each of these things and figure out what particle we've gotten rid of. Okay, so hopefully that was okay for you guys. Why does the graph stop here? It stops because PB206 is stable. If things are stable, they're not going to change. All right. Hope this was okay. I will see you guys tomorrow and we'll do a lot more practice.